show 5a, let us solve 5a by applying the first strategy. So show for any x greater than or equal to 0 that the total claim amount from time s to t has the same distribution function as the total claim amount from time 0 to t minus s. So if any of you were at the class, you will probably know that I started by tackling the case x equal to 0. Now there is actually no specific reason theoretically why we have to tackle the case x equal to 0, because it's actually included as long as we just look at the distribution function. But just for good measure, I think we should look at the case x equal to 0 separately in the end, just so that we understand the way that S is built. But yes, so let's just look at it in the beginning already. So, for example, let's just write if x equal to 0, then what do we have? Well, then the probability that the total claim amount is less than or equal to 0, well, that is just equal to the probability that it is equal to 0, right? Because the total claim amount is not negative. So when is this equal to 0? Well, the thing is, we have that S from time s to t, well, the total claim amount is equal to 0 if and only if there have been 0 claims between time s to t. I'll just put this inside stars here. So that means that this event is equal to this event here, which means that they have equal probability. So the total claim amount is equal to 0 if the total number of claims is equal to 0, and that has the same probability as, so this is this equality, and if I carry on, then because of stationarity of the homogeneous Poisson process n, then we know that this probability here is just the same as the probability of no claims from time 0 to t minus s, right? Because it's a homogeneous Poisson process, so the number of claims from time 0 to t minus s has the same distribution as the number of claims from time s to t. And then this thing here, well, we just applied the same logic to conclude that this, well, if there are no claims from time 0 to t minus s, that also means that the total claim amount from time 0 to t minus s is equal to 0. So these two events are actually equivalent, so they have the same probability. And then actually we are done. Then we have shown that at least for x equal to 0, these two are equal. And again, now I will just erase this because, oops, don't know what happened there. Did I zoom in? How the heck do I zoom out? Just a second. Oh, okay. So, I'm working kind of a new tool, so I'm not really sure how this works, but now we're good again. Okay, so I'll just erase this here because actually it's enough if we just consider all x is greater than or equal to 0 at once. So let's take a look at this and try to start calculating. So let's start by looking at this one. We look at the probability that the total claim amount from time 0 to t minus s, change to a lighter color, Look at the probability that that is smaller than equal to x. Okay. Well, let's start by plugging in the definition of the total claim amount here. That is the sum of claim sizes up until the n of t minus s claim. And since this n up here is kind of interfering with the way we can work, let's use the double expectation property to just sort of try and condition it out. So what we're looking at here is so you guys probably have seen this from insurance and law. So we take this probability and we condition it on the variable n of t minus s and take the mean value. And what does that actually mean? Well, that means that since n is a discrete stochastic variable, what we're essentially doing is we're taking the mean value of each of these for each different outcome of n of t minus s. So let's start by writing up the different outcomes that we have. So n of t minus s, I equals 1, xi smaller than equal to x, given that n of t minus s takes on a different outcome k equal 1 or 2 or 3, etc., etc. And then since we're calculating the mean, I'll multiply with the probability that n of t minus s takes on that outcome, k. And since n is Poisson distributed, k can attain values 0 up to infinity, right? So here I have written up the mean value of this conditional probability. Now what is this equal to? One of the first things that we can just consider here is that this thing that we have here, this thing here, is actually not so mysterious, right? This is just a probability of one event given another event. So essentially what we have is that we want to look at what is the probability of A given B. Well, that probability is the probability of the intersection of A and B divided by the probability of B, right? So let us just try to calculate that directly inside here. So we have the sum from 0 to infinity, and then I have the probability that xi is smaller than equal to x, for I going from 1 to n of t minus s, intersected with the event that the number of claims from 0 to t minus s is equal to k, divided by the probability that the number of claims from time 0 to t minus s is equal to k. And then I also multiply here with the probability that this is equal to k. So normally we actually do the calculations a bit faster, but since it's the first time we're doing this, we're going to go a bit slower. So the thing is, like normally what we're going to say is just we'll say, oh, look at this, x and n are independent because we have the assumption that they are independent, hence I can just take this value k and put it here. Problem with that is then you guys don't know exactly what is going on behind the background. So let us just write up this definition here, and then we can actually see exactly what's going on. Because since xi and n, they are independent, we then have that we can split this up into two things in a second. So let's just look at this event first. So I think maybe the best way to do this is to look at it over here. So if we look at the denominator, at the numerator, we have the probability of this event inside. But the thing is, if I look at the event xi smaller than equal to x, summed up until t minus s, intersected with the event that n of t minus s is equal to k. Well, that is the same as the event that I have k up here in the sum intersected with n of t minus s is equal to k. Because in this event up here, the top boundary of the sum can't be anything else than k. So the thing is that I can write this probability, if I just call this probability here, if I call it star, I can write star is equal to the probability that I have k here, smaller than equal to x, intersected with the event that n of t minus s is equal to k. However, we do assume also that x and n are independent. Hence, I can split up the probabilities into a product. And this then allows me to look at the numerator. Then I have a product of two probabilities, right? And the thing is that with this probability here, this one here in the numerator, it will cancel out with this probability in the denominator. So, summa summarum, what we have is the sum from 0 to infinity of the probability that the sum of xi's up until k is smaller than equal to x multiplied by the probability that n of t minus s is equal to k. Okay, so now we will take a break, and then I will continue in the next video with this, because what we have shown now is that the probability that the total claim amount up until time t minus s is smaller than or equal to x is given by this expression. In the next video, we will show that the probability that the total claim amount from time s to t is smaller than or equal to x. So in the next video, we will show that this thing here is also equal to this. But that will come in the next video. So, see you in the next video.